Hey, welcome to another AI mini lecture. Today, what we want to study is the iterative deepening search. So this is a kind of DFS. It's called iterative deepening search, but it's DFS with a twist. So let's dive right into it. So firstly, why do we need iterative deepening DFS? Before we do that, let's remember what DFS and BFS stands for. So in the AI, when we have two different kinds of search algorithms, DFS versus BFS, if you recall, what DFS does is a depth-first search. You go to a node and you start diving further and further into it. In the breadth-first search, you kind of go in a more organized way from top to down, but you first go to the first layer nodes, second layer nodes, third layer nodes. Perhaps this visual might help. Let me share the screen and walk us through it. So this is the depth first search. In depth first search, we would start from this root node, and let's suppose we are looking for this goal node here, these nodes that meet the goal test. We would go from this source node, this root node, go to this particular, and we keep going down as far as the depth will allow. And once we keep coming back up, then we'll go down again. We'll go back, we'll go down again, but from each node, right? And then once we finish all the way up, then maybe we go to the next successor of the goal of the root node. Again, we go down as possible, then maybe go back up, go down, go back more up, come down. But this is the way that we traverse the entire graph here. So this is the depth first search. If we follow what is the time is going to be b power m, where b is the branching factor, how many successor nodes are there for each node. If there are multiple different, you can take the maximum. And how many tiers, what is the search height here? So that's b power m total time. But the space, if we want to track the space in DFS, what we look at is we look at all the nodes from top to the height here. And then each node we might have to track, okay, we have these other nodes that we have not yet visited. So the space on the fringe, the kind of space requirement that the DFS algorithm has, is of the order of b times m, where b is the branching factor, might be constant, may not be constant, but it's b times m. So that's the space. Let's go into BFS. So in BFS, we traverse this graph in a slightly different way. We go from top, we go to the first level nodes, we go to the second level nodes. So we traverse this graph layer by layer. Now in this case, the search time is somewhat the same, but the time, now one difference you can already see is that compared to DFS, DFS might not find this node here, it might find this node here, because it traverses some left sub prefix of the tree, whatever definition of left is. So it would not see this goal node, rather it would see this goal node, and it might report that this is the closest goal node, in which case it would be wrong. While in the case of BFS, by definition, it is going to find this goal node first. So it'll find the better goal node. The problem though with BFS is that the amount of space that it has on the fringe is roughly how many nodes are here at each layer, which can be exponential. So that's b power s, b in each, b square, b cube. So b power s, where you're looking at s tiers. All the maximum height, that would be m tiers, that would be b power m. So that's the key difference between DFS and BFS. Now what we try to do is, we try to combine these two solutions into one, and that's called the iterative deepening. Iterative deepening IDS, iterative deepening search, or sometimes we call it iterative deepening depth first search. So it is still depth first search. So we are kind of going to do depth first search here. But what we will do is we'll limit the search height to 1. Then we will limit the search height to 2. Then we'll limit the search height to 3. And we will iteratively increase that search height. So that's referred to as iterative deepening, IDS. And the main advantage is that the overall space complexity is that of the DFS, because that's the DFS that we are using. So it remains b times m, does not go exponential. So if you're running out of memory, iterative deepening search could be a very, very, very good alternative to BFS. And you will still be able to find the shortest cost path, the shortest distance path from the root node to the goal node. and you will have the advantage of the DFS. And now there can be a question whether this can really be a lot of wasted computing. It does appear like that because you're going to do search up till height 72. Then next time you're going to search up till height 73, and you're going to repeat the search from 70 up till 72 and do it again. However, practically speaking, more work happens at the bottom layers. So it is actually not so bad. And you can do a little bit more analysis of this to say that most of the work is happening in the last layer. And last layers, they come later. So the amount of overhead that you're going to do is actually not so bad. So for that reason, iterative deepening search is a core concept, one of the main tools that you would often have in your kitty to use against some of these search problems. Hopefully that's helpful.